spoke about open sets. So an open set is open if intuitively, what does it do? It protects all the members within it. So an open set is a perfect defense set. But make sure you don't call it a perfect set, because a perfect set is something else. We will learn that as well. So an open set, it is open if for every x. What is it mathematically? If for every x, there is an open ball. You might write it as there exists a ball of radius epsilon, and this epsilon depends on x. In other words, you might have to select small ball or a bigger ball depending on the particular x you have around x. This set is, if you remember, it only means all the y in M, such that the distance between x and y is less than this epsilon sub x. And this set is inside, this time call it U. It's inside U. And what this means is that, well, if this is my set U, then of course the black boundary that I drew, it's not part of it, but really if I select this x, I can select the neighborhood to be as big as, let's say, something like this. So that's my b epsilon sub x around x. But if I picked another point, so let's say if I picked this point right over here, the ball that I can select is much smaller. And that's why this would have been maybe b epsilon sub y centered at some y. You see what I mean, right? So all that it means if a set is open is that every point in it is the center of some open ball, which is itself part of the set, of the region. And we saw examples of open sets. And now we follow with proposition. So proposition, we would say that an arbitrary union of open sets is open. Now, do you see why that must be the case? When I take unions of open sets, it's like I'm taking the unions of the bubbles that make them. So basically, what is the set? It's a set that is built up of many, many bubbles. And each bubble contains in its center a point of this U. So this theorem, in that sense, will be obvious. But let's prove it. Proof. So suppose that U is equal to some union over some index alpha of, well, let's say V alpha. Where the alpha is open for each alpha. So you see what I mean by this alpha? I do not know if this union is countable. So alpha is some index. Maybe it's an index that goes over all real numbers. Maybe it's an index that goes over something else, but it's an arbitrary union. Could contain uncountably many things that you put together. So why would you be open? Then, for any x which is part of U, any x which is part of U, x is part of V sum alpha. for some alpha. Make sense? If I have something in U that came from one of the things that I put together, and now how do I prove that this X is protected within U? What do I do? You see? Those sets are protecting sets. They protect the members within them. How do I know the union is a protected cell?
Pick an arbitrary X.
That's what we did. We picked an arbitrary X. And then we want to do what?
There's a radius around it.
Yes. Find a radius around it, a ball around it. And what about this ball? It's contained in U. So how do I know? How can I pick such radius? Hence what? How do I pick the ball?
Maybe the ball where it came from.
The ball where it came from. So hence, there exists a ball of some radius r around x, which is wholly contained in V sub alpha, because it's open. Because V sub alpha is open. I'm not going to write it's open, you should obviously see it. It's open, that's the condition of being open. And what's the implication? The implication is that we have ball of radius r around x, it's a subset of the alpha, and the alpha is a subset of the unions over all alpha, which is U. So it's trivially so. We're done. Okay, so that's one proposition. How do we fare with intersections? So this is unions. How about intersections? If I take an arbitrary intersection, if I take arbitrary intersection of open set, do I get an open set or not? So how many of you say yes? Just take a bunch of intersections, you always have. So no matter what intersections you would have. Okay, one person, two, oh see, more people are gaining confidence. 1, 2, 3, 4, 5. Well, you were inspired. So let's see. So proposition, I'm gonna say given finitely many. Many sets V1 open sets, I should say. V1 through Vn in symmetric MD. The intersection is open. Why is it the case? Also notice I'm proving right now not an arbitrary intersection, but only a finite. Okay? So if I take this intersection, well, let's pick an x belonging in U. So pick x in U. Then x belongs to V1, it also belongs to V2, it belongs to Vn, it belongs to all of them. And each of them has a protection. So therefore, we can say that ball of radius R1 around x will be entirely a subset of V1 ball of radius R2 around X will be entirely a subset of V2, etc. For the appropriate R. You understand what I'm saying, right? So each of those are open, so each of them has an open ball in V1, an open ball in V2, etc. So then how do I take a ball that will be in U, in the intersection? So let R equal to what?
The smallest part.
The smallest. If R equal to the minimum of R1 through Rn, then ball of radius R around X is a subset of ball of radius Rk of X, and therefore for all X, for all K, I'm sorry, which implies that the ball of radius R around X is fully inside of U. So it's inside of all of them, it's part of the intersection. So we have shown that each X has some protection. So you see that intersection is union actually increases protection. You agree? So if you union, you might still have the same radius of protection, but in fact it might even grow. So the union only increases protection, but taking intersections chips the protection away. Because what you see here, you have to reduce the radius. So you have to surround yourself potentially by smaller and smaller neighborhoods. Which is why in the first one we only have one radius, we have br of x, whereas here we have to specify particular radiuses, radii. Right. In each field. So, remark, an arbitrary intersection of open sets might not be open. It might be open, it's possible, but it might not be open. Might not be open. And here's, for example, each minus 1 over n to 1 over n is open in R. Yes? Yet, if I take the intersection where n starts from 1 to infinity, so I take a countable intersection, not even arbitrary, but countable intersection, 1 over n, minus 1 over n to 1 over n, this intersection is what? What will it equal to? What survives in this intersection? Not quite. Something null set means everything is deleted. If everything is deleted, the empty set is open. Do you remember that? The empty set is a protective set by default because it has no one to protect. So there is no one in the empty set that is exposed, that is not protected, and that's why the empty set is open by default. What's the intersection?
0.
Exactly. Only 0. Look at it. So I have minus 1, 1. Minus 1 half, 1 half, minus 1 third, 1 third. You squeeze and you can see that every negative and every positive number is deleted, right? So the sets are nested. Minus 1 to 1 is the biggest of them, and all the others are just inside. So the intersection is just you zoom in, and what survives is 0. And that's, you see, 0 is exposed from left and right. Not open. And when I say not open, you always remember it's a relative property or relative to R. You understand what I mean? So for example, if I ask you, is the set containing 0, is it an open set? Unless by default I'm talking about R, my question is meaningless, because I can use the discrete metric and everything is open. Or I can use the regular metric and then it's not. You have to know what's your set and what's your distance function. Okay? So here is another theorem. So this theorem is describing the open subsets of R. So characterization of the open subsets of R. And this is saying the following. If U is open, then U is the countable union. By that I mean there is only one countable union. There is no several types of countable unions. Only one countable union of disjoint open intervals. Proof. Proof. So for x belonging to U, so I take x in U. And x is necessarily on the number line. Okay? So what I imagine doing is I imagine going with a broom. That's what I personally imagine. I go with a broom and I see how far can I extend with my broom, how far can I extend the line of the interval to either left or right from x. Does it make sense? So you see, I'm in this space. I want to create for myself the biggest possible bubble such that I still remain within U. That's the idea of this construction. So for x belonging to U, here is how we do. So we consider the sets. Consider A to be equal to infimum of somebody is not happy about infimums. Huh? I heard something, not again, not infimums. So infimum of what? Of the set. So maybe I'll go with U sub x. Okay, so it depends on x. It will be the infimum of sets of the form A x, where x is included. So it will be the infimum of all the A belonging to R, such that the interval A to x, where A is excluded, x is included, is subset of U. Okay, so this means going with the broom to the left. Okay, so if I go to the broom with the broom to the left, I sweep. I get? Okay, that will be a sub x. And it could be minus infinity if I can go forever in that direction. And I will let b sub x equal to the supremum of the set B belonging to R, such that x to B is a subset of U. Okay? Then you can say that the interval Ix, which is the interval from Ax to Bx, is going to be a subset of U. You see this? It is going to be a subset, since that's kind of what happens, right? I push a little bit, it's a subset, I push a little more, it's a subset. Now the point Ax cannot be part of U, right? It's the biggest I can go, because if Ax, if it's part of U, then it can be protected, then I could have extended it further. Do you see this? If A of x were part of U, then U is open, so then I can select an open neighborhood around A sub x, and that means I could go further. Okay? So it means that this is the biggest I can have.
Why can't you just say it's the infimum of the set you're talking about? I guess U. Why do you say it's the infimum of that range?
Well, I do not know that U is one whole interval, so maybe U is just a bunch of intervals. So if I'm stuck in one bubble, I will not be able to extend it. I will not be able to expand the bubble throughout all of U. But there might be other bubbles disjoint from it. So this is basically like I'm exploring the biggest connected bubble, the biggest one open interval, one open ball within U. So you understand what I do, right? So I locate myself somewhere, so then I explode. How far can I go to the left without being in danger, without escaping the protective set? How far can I go to the right without escaping it? And clearly, I can justify it if you want with more arguments, but I think it's pretty clear that you generate the biggest possible bubble that you have for x. The biggest possible bubble that contains x, that's how you can generate it. Okay? So you might say that Ix is maximal. And why I leave it to you to consider. It's maximal, right? I definitely cannot contain b of x, because if b of x is part of U, that means it's not the supremum. I could have gone further, because b of x will then be itself protected. Okay? So b of x is not part, a of x is not part, I cannot possibly extend this open ball any further. Okay? So that's what we know, and then then the next thing that we observe about such intervals is given x and y belonging to U, we have either one possibility is that I of x intersection with I of y. So in other words, if I start at x and I do this expansion, and I start at y and do this expansion, either those bubbles are disjoint, so they contain nothing in common. And the picture is something like this. So here is x. I started somewhere in x, and I extended to the left and right as much as I could. So that's my I of x. And this is I of y. So they are disjoint. Or I of x equals I of y. Right? So if they overlap, if they have one point in common, that means I can extend them together to one whole bubble. Right? If those bubbles were to overlap, then they are part of that one same bubble. Okay? So what we now can do is, so this means therefore therefore the set of I of x, the set of therefore maybe I should say the collection of distinct I of x is countable. Now, why is it countable? I'm claiming, so you see that we have a bunch of them. So if I consider, so for a bunch of different x's, I will generate the same bubble. So if I select an x here or here or here, any point I select within this interval will generate the same set. Okay? So I pretty much generate all the possible bubbles, and then I select all the ones that are distinct. How can I claim that the ones I have are all countable? Do you have an idea? They are disjoint, right? So the ones that remain, they are disjoint. How do I know they are countable? Yes, please.
I just want to ask, can you give an example of a U that has two distinct open subsets?
Plenty. Right, so hold it, I'll finish this slot and I'll give you that example. You remind me if I somehow forget about it. Right? Hold it and I'll draw you a bunch. So how do I know it's countable?
Maybe you can create like a bijective map with the natural numbers. You just have one.
How do I do it? So good, but how?
Say Ix is 1. The other one is 2.
And how do I know I can create it? What do intervals always have? What do each interval has? Each interval has definitely a bunch of points between them, but in particular, what type of points in R do we have in an interval? A rational number. Rationals are then, do you remember that? Between any two real numbers, we proved it. By Archimedean property, we proved that if I have two real numbers, no matter how close together, we can push them apart to put an integer. And then that means that in the original interval, you had a rational number. So no matter how small, it contains a rational number. Now the rational numbers here are distinct from the rational numbers in here. So each interval can be represented by a rational number that will not be found anywhere else. So I will say this. So each I sub x has a rational representative that is not found in any other disjoint I sub y. You understand what I mean? So if this is I sub y and this is I sub x, I can pick for each of them one rational number. And in this I pick one rational number. So now each interval is represented by a rational number. So the indistinct intervals I have are all represented by some subcollection of rational numbers, but any subset of rational numbers is countable. Yes? Any other disjoint I sub y. Hence, the collection of Ix, maybe I will say Ix distinct, is in one-to-one correspondence with a subset of rationals. Hence countable. must be countable. So then example of such sets, as I was asked. So well, you can take this. Take U to be the union from, let's say, n equal 1 to infinity of the intervals 1/2 to the power. So I'll say like this, maybe n minus 1/2 to the power of n to n plus 1/2 to the power of n. So such intervals. So this is a countable union. For example, how does this open set look like? So it looks like this. So you have the number 1, and then this is an interval of size 1/2. Then here is the number 2, and it has size quarter, and then somewhere here is going to be 3, and that's even tinier. Size 1/8, so on. So this is a union of bubbles, and each of them are distinct. Okay? Make sense? So while we're at it, do you remember that problem about the, did I mention about the driver? Remember the ice road trucker, was he speeding? So in the problem you had, the way I set it up, you had this car, or maybe a truck. Okay, so you have this truck, and the position here is 0, the position here is 60, so 60 miles, and the speed limit is and the speed limit is 55. Let's say you can make it even 59.9 if you want to. So the speed is 55. Okay. So the problem was he's getting a ticket. But because the police officer accuses him of speeding. Remember that? But all that, I mean, I'm not sure what was known in the actual situation, but all that I assume to be known is that there was a camera in station A, so this is station A. This is station B, which is 6 miles down the road. And you know that his position at time 0 is 0. So in other words, at 0 hour, that's the moment when he's at the station, he's there, and his position 1 hour later is 60. So this means 1 hour later. Okay, so all I know is that he was here at the beginning, and 1 hour later he's at 60. So the question is, was he speeding? And speeding means at any moment exceeding the allowed velocity. Remember this question, yes? So, did you have a conclusion? I forgot. That was a while ago. Did you have a conclusion? Was he speeding or wasn't he?
He had to, because of calculus.
You see, he had to because of calculus, right? And now we're in some position.
Mean value theorem?
Yeah, the mean value theorem. Thank you for remembering. So at the speeding, the argument that some people present, let's say from calculus. Remember, from calculus we said what? We said we have that P if we assume that P of t is differentiable. If you assume that P of t is differentiable, in other words, what this means is that speedometer always shows the instantaneous velocity. If we assume it's differentiable, and we assume that it's continuous, actually differentiability implies continuity everywhere. So if I assume that it's differentiable, then by mean value theorem, we know that P prime of t0, I don't know what time exactly, should equal to P of 1 minus P of 0 divided by 1 minus 0, which is 60. So that's 60 miles per hour. And therefore, by calculus, he was speeding. But calculus assumes that we are dealing with the real number line. Okay? Remember that, right? Calculus assumes we are dealing with a number line. But what I mentioned is that even under looking on the microscope, because rational numbers are dense, because between any two reals there is a rational number, if you now were to delete all the real numbers, who would have noticed? Right? All real numbers are deleted, you can zoom under a microscope, looks exactly the same, no difference. So this truck driver needs to call a Jewish lawyer. So the Jewish lawyer will do what? He will say the following. But how do we know? But how do we know that? But how do we know that the road is real? How do we know that? Right? So in other words, maybe the road is an interval in Q. So maybe it's a segment from 0 to 60, but inside of Q, maybe. You understand what I'm saying? And what's the consequence then? This is countable, so then I can say that, let's call this interval I, okay? Then I can be written as union from n equal 1 to infinity of something like this, of the open interval Qn minus epsilon over 2n plus 1 to Qn plus epsilon over 2n plus 1, where Qn is the enumeration, where Qn, the sequence, is our I. You see, all the points in here are countable. Therefore, I can list them in whatever order, 1, 2, 3, 4, 5, and each point I can contain in an interval of whatever arbitrary size epsilon over 2 to the n plus 1. Okay? You understand what I'm saying? So what I'm saying is take this road and take a bunch of points on the road. Here is one point. Not only do I take the point, I even surround it by an open interval. So I take another point, I surround it by a smaller interval, another surrounded by a smaller interval, etc. In fact, the intervals might intersect. Okay? They might even intersect. And then let's measure how far has he traveled. Did he have to travel 60 miles? Well, the length of this interval of this interval is less than or equal to the sum of the over the lengths of the segments that possibly even overlap, right? Is less than or equal to, let's call this I sub n. So this I'll call I sub n. So length of I is less than or equal to the summation, the infinite sum, where n equals to 1 to infinity of the lengths of I sub n. And what is that equal to? That's the summation where n goes from 1 to infinity. So the distance here is, it's simply this minus that, so it's going to be twice epsilon over 2 to the n plus 1. And what's that sum? This sum is epsilon over 2 to the n. Now if I add epsilon over 2 to the n, what do I get? I get simply epsilon. So what did I conclude? For any epsilon, I can subdivide, chop this road into small enough pieces, possibly with overlaps, and if I add the lengths together, I get that the length is less than epsilon, for any epsilon, which means that the length of this road is 0. You see, this is where I use, although they're not quite disjoint, they don't have to be disjoint, but this is an open set, right? I covered this interval by a bunch of bubbles from an open set and use that to calculate my measurement. So the implication is length of I equals 0 because it's smaller than any epsilon.
Question, did you just pick the e over 2 to the n plus 1 so that in the end it would work?
Well, I basically what I'm saying is that however you measure the length, the sum of the parts does not add up to, you see, so you might try to measure the length by taking 60 minus 0 and say it's 60. But I'm saying, well, chop it up into infinitely many segments and then those segments might be overlapping. Your intuition tells you that the sum of those measurements should add up to 60, but this is saying it adds up to 0. So not only was my client not speeding, he was such a marvelous driver that he did not travel any distance and arrived from the station A to station B without even pressing on the gas. Stage dismissed.
My question is, where did epsilon over 2 to the n plus 1 come from?
This is only to make it neat and make it equal to epsilon. So look at it, right? So take this point minus that point, it will end up this q and cancels out, and it ends up being just twice this number.
So it's a
and
radius.
this 2 cancels one of, so that's why I have n plus 1. It cancels one of them, so now it's epsilon over 2 to the n, and this neatly sums to epsilon. If you chose other intervals, it will sum up to, again, a tiny number. The point is this can be made arbitrarily small. I can select smaller epsilon, that will work. Yep.
How would you split an open ball into disjoint intervals?
I didn't say I split an open ball to disjoint intervals, but that depends also on this. What open ball do you have? So if it's in Q, you might have this situation. So you might have the open ball from 0
I'm asking because it says
to 1.
the union in R.
Any.
Sorry. If U is open, U is the countable union. If U is an open set, then U is the countable union of disjoint open interval.
Well, what I mean at most countable. So, what you mentioned is quite right. So you understand that in the theorem that I stated, if it happens that it could happen that I just have one open ball, and that's it. And when I say countable, I'm using the loose sense of the word. I'm just saying it might be 1, 2, 3, 4, or infinite, but countable infinity. Aleph no infinity. Okay. So that's so very very right. So when I use the word countable here, I meant at most countable, to be precise. Okay. So it's either 1 or if it's just one open interval, I do not split it. If it's 2 disjoint open intervals, I don't split them. But the point is that any open set will be at most countable union of unsplittable open intervals. Okay. So what I was drawing, it was not the answer to your question. Okay, good. Yeah, you see, I don't know, it's maybe a sign that I grew older. People used to be, oh, they were very excited about it. Maybe I tired of it. But it's new for you, I think. You should be excited. What generation are you? X or what is it called now? Y? Ah, you are Y. Yeah. I'm in the generation Y. I just ask why God? Alright, so let's finish up with open sets. All I need to do is, so there is a trinity. So it's like St. Patrick's Trinity. You have, what is it? You have the Father, the Son, and the Holy Spirit. What do we have here? We have the open sets, the closed sets, and sequences. Okay, so there is always this Holy Trinity in analysis, and we want to describe open sets right now in terms of sequences. So open sets in terms of sequences.
Do you mind writing the Father Holy Spirit?
No, I mean I don't know what trouble I'll get into at some point. Open sets in terms of sequences. Okay? Open sets in terms of sequences. By the way, topology, a word that I sometimes loosely throw around, topology only means what are your open subsets. Okay, so you have a structure in your space, and if you can describe all the open sets, that's going to be called a topology. Okay, so in this case, we're only studying topology with metric spaces, so different metrics might induce different open sets, but not always. So it's, for example, the discrete space induces that every subset is open. But there will be other metrics that make fewer subsets open. Okay? So open sets in terms of sequences. This is almost trivial to mention. So you might say this. So if U is open and U open, and we have X is an element of U, and Xn. Sorry. And Xn goes to X under the distance D. So you understand, when I say U is open, I'm just lazy. There is a metric space, ambient metric space, and I have a sequence Xn going to X. So what does it mean? It means that it implies that Xn is eventually in U. And by that I mean this. So if this is the set U, and this is a point X to which I have a sequence convergent, so I might, it's like trying to visit a Polish neighborhood, right? So you go and you go in the dark of night, and you approach, no way, right? As soon as you're in, they are gonna open the windows and right? That's inspired actually. When my neighbor used to be Polish, I couldn't go to the house, and the neighborhood balcony actually had the door open. So I pulled myself up to the neighborhood, and she's like a scared crow. She's like, maybe she thinks somebody is robbing her, right? So this is exactly what I think of when I think about the sequential characterization of open sets. You cannot go to visit X without the neighbors knowing about it. No way about it. Right, so here. Here. Okay, so you are eventually, see, if you delete a bunch of terms of the sequence, you are inside of the set U inside of the neighborhood. They are all turning on the light.